Physicists widely agree that the universe began with an event known as the Big Bang, roughly 13.7 billion years ago. Yet one fundamental question remains unanswered. What caused this cosmic explosion, and why did it happen? Over decades of study, the Big Bang theory has remained the leading explanation for the origin of the universe. Thousands of scientists have contributed to this research, and the evidence gathered has consistently supported this model. According to the theory, a mysterious force called dark energy, far more abundant than visible galactic energy, has driven the universe's expansion since that primordial event. However, science is constantly evolving. With technological advancements, new discoveries often challenge long-held beliefs. One such challenge has emerged from the James Webb Space Telescope, JWST. Renowned astrophysicist Michioku has publicly questioned the Big Bang model, prompted by JWST's unexpected findings, the detection of over 750 new galaxies that don't fit existing theories. These discoveries are reshaping our understanding of the cosmos. Join us as we journey beyond the observable edge of the universe to explore these groundbreaking revelations. If you're passionate about space and cosmic discoveries, subscribe to our channel, like this video, share it with others, and turn on the notification bell to stay updated. The images captured by JWST are breathtaking. Hundreds of galaxies visible in a single frame, each revealing stunning beauty and cosmic depth. But while these visuals may simply awe the general public, they have caused considerable concern in the scientific community. Why? Because what's being seen doesn't match the predictions made by the Big Bang theory. In fact, the new galaxies are far more numerous than expected, and they exhibit surprising features. They're smaller, older, and smoother than current models suggest they should be. One scientific article even used the word panic in its title, highlighting the intensity of the disruption these findings are causing among cosmologists. For decades, the Big Bang has served as a cornerstone theory explaining how our universe began. But the data now emerging from JWST challenges that foundation. These newly observed galaxies contradict essential assumptions of the Big Bang model. They are 2 to 3 times smaller than similar galaxies previously seen by the Hubble Space Telescope, a contradiction to what we'd expect in an expanding universe, where distant galaxies should appear larger due to cosmic stretching. Furthermore, these galaxies appear unnaturally smooth. According to the Big Bang theory, early galaxies should be chaotic, irregular, and full of structural complexity as a result of rapid formation and gravitational interactions. Yet JWST reveals galaxies that are remarkably well-formed and serene, a direct contradiction to what science predicted. In short, these observations not only question our understanding of how galaxies form and evolve, but they also shake the very foundation of how the universe began. Could it be time to rethink the Big Bang? Only time and further exploration will tell. At the very beginning of the universe, all matter, energy, and the fundamental components of the cosmos were compressed into an incredibly dense point known as a singularity. In this state, density reached infinite levels due to the extreme compression of everything that would eventually form our universe. This concept of a singularity is rooted in our current understanding of physics, particularly Albert Einstein's theory of general relativity. Within the singularity, matter and energy existed in an unimaginably compact form. The mass and energy were concentrated into an infinitesimal space under enormous pressure and temperature, far beyond anything we can observe or replicate today. This superheated, high-energy point contained the seeds of the entire universe. The singularity marks the origin of everything, the very beginning of space, time, matter, and energy. Following this, the universe began expanding in an event known as the Big Bang. This expansion unfolded over roughly 13.7 billion years, shaping the cosmos as we know it. One of the earliest phases of this process was cosmic inflation, a mind-bogglingly rapid burst of expansion that occurred faster than the speed of light. During this brief period, space itself stretched at an exponential rate. Cosmic inflation played a crucial role in shaping the large-scale structure of the universe. It smoothed out irregularities, distributed matter and energy evenly, and laid the foundation for the formation of galaxies, stars, and other cosmic structures. As time progressed, the rate of expansion slowed down, though the universe continues to expand even today. This ongoing growth is referred to as cosmic expansion. One key piece of evidence supporting this is the redshift of light from distant galaxies, where light waves are stretched, moving them toward the red end of the spectrum as space itself expands. During the early stages of expansion, all the material in the universe was packed into an extremely compact volume. Matter couldn't exist in such a state. So as the universe cooled, it underwent transformations. Particles such as protons, neutrons, and electrons formed and began interacting with surrounding light and energy. These interactions led to the creation of matter through a process called nucleosynthesis, which took place in the first few minutes after the Big Bang. Astronomers initially expected to observe chaotic, disorganized galaxies resulting from frequent cosmic collisions. However, the James Webb Space Telescope JWST has painted a surprising picture. Instead of jumbled structures, JWST images reveal well-formed disks and spirals, much like the galaxies we see today. This challenges a belief that mergers are common in galaxy formation. If these early galaxies haven't experienced many or any mergers, it suggests they may have formed large and organized from the start. Additionally, the idea that galaxies should appear smaller due to the optical illusion caused by the expanding universe doesn't hold up under JWST's observations. This contradicts predictions made by the current cosmological model. Even more striking, the age and number of galaxies detected by JWST further challenge the Big Bang theory. The telescope's advanced infrared filters allow astronomers to study the colors of distant galaxies, data that helps estimate their age. Surprisingly, many of these galaxies appear older and more developed than expected, raising questions about the timeline and accuracy of the Big Bang model. Don't miss our next update as we dive into the latest mind-bending discoveries from the James Webb Space Telescope JWST, findings that could fundamentally rewrite our understanding of the universe's origin. As astronomers continue to sift through JWST's enormous data troves, new models are emerging, some of which may one day replace or significantly reshape the Big Bang theory. Among these are proposals for a steady state or cyclic universe, where cosmic history unfolds in repeating cycles of expansion and contraction. Other ideas delve into realms like quantum gravity or multidimensional space-time, offering alternatives to the single, explosive beginning we've long accepted. What's clear is that we're standing on the threshold of a new era in cosmology. JWST isn't just confirming what we thought we knew. It's challenging foundational assumptions and unlocking new frontiers in theoretical physics, astronomy, and even philosophy. Questions once dismissed as purely metaphysical, such as whether the universe had a beginning or whether it will ever end, are now being approached through scientific observation and empirical analysis. This scientific revolution reminds us of a key truth: science evolves. What we accept as fact today could be seen as incomplete or entirely incorrect tomorrow. But that's the essence of discovery. By continuing to ask questions, explore the unknown, and revise our models, we stay true to the spirit of scientific inquiry. As we peer deeper into space, we are also looking further back in time. Light from distant galaxies has traveled billions of years to reach us, offering glimpses into the early universe. But what we're seeing doesn't always align with Big Bang predictions. Galaxies appear to have formed earlier and in smoother structures than expected, prompting scientists to question long-held beliefs about cosmic evolution. Some researchers argue that this doesn't disprove the Big Bang, but reveals gaps in our understanding of how galaxies form and evolve. It may be that galaxies emerge more rapidly or under conditions very different from what current models suggest. Others speculate that we could be seeing signs of unknown physics, forces or particles we've yet to discover. Even the concept of cosmic inflation, a rapid expansion shortly after the Big Bang that supposedly explains many early universe anomalies, is now being scrutinized. If early galaxies are too mature or orderly, inflation may have occurred differently than we thought, or perhaps not at all. This has reignited interest in alternative models once considered fringe. These include the ekpyrotic model, which proposes a universe began from the collision of higher dimensional brains, and conformal cyclic cosmology by Roger Penrose, which envisions a universe undergoing endless cycles of death and rebirth. Though controversial, these models are gaining attention in light of new data. Meanwhile, advances in telescope technology, ultrasensitive sensors, and data analysis tools including machine learning and AI, are enabling researchers to detect patterns and anomalies in cosmic data that would be invisible to the human eye. These technological breakthroughs may prove vital in interpreting JWST's revelations and shaping the next generation of cosmological theories. One thing is certain: we are witnessing a transformative moment in astrophysics. The discoveries coming from JWST are more than scientific achievements. They're philosophical challenges. They urge us to reconsider humanity's place in the cosmos, the nature of space and time, and even the definition of reality itself. As we await more peer-reviewed results and future observations, we must approach this new frontier with both skepticism and curiosity. Science thrives in the space between doubt and discovery. The universe doesn't have to conform to our theories. It's up to our theories to evolve and reflect the universe as it truly is.